to make this whole thing balance. And the trick is we're going to take a vertical line and we're going to figure out how to get a left-right balance with the vertical line. We're going to take a horizontal line. So we're going to take a vertical line like this, and this is going to give us the left-right balance. And then we're going to take a line like this, and that'll give us the front-back balance. So we're going to find a knife that'll cut it this way to get a balance, a knife that will cut it this way to get a balance. And the intersection of those two is going to be the single point that has the left, right, and the back, forth balance. So what we're going to do is we're going to get two lines. We're going to get this horizontal line where y is equal to some unknown y value. We're going to get this vertical line where x is equal to x bar. And then this intersection point right here is going to be the balancing point, which we call the centroid. So far, so good? When we're going to get x bar, it's just like we had before. It's the sum of the moments about x equals 0 times the sum of the weights. Well, the weights are 8 plus 4 plus 3. And for the moments about x equals 0, calculation is going to be the distance from x equals 0 times the weight. X equals 0 is this vertical line. And then what I've got is 8 pounds at 3.2, 4 pounds at 2.1, and 3 pounds at -1.1. So this 8 pounds is at the point 3.2. How far is this from the line x equals 0? See, it's 3. The horizontal distance, so it's 3. So I've got 3 times 8. And that distance is 2. So that means for my numerator, I've got the 2 times 4. And then, this one's a little bit interesting. What's that distance? It's not 1. It's -1. Remember, we're doing sign distances here. So things to the left are negative. And so that would be 3 times -1. So whatever that comes out to, it's going to be some decimal, is the x-coordinate of our balancing point. Or another way to say it is that if I ran a knife like this, it would balance in the left-right direction. I'm going to waffle back and forth between calling the denominator the sum of the weights or the total weight. But I do want to emphasize that denominators for x bar and y bar are going to be exactly the same. The numerator here is the sum of the moments about y equals 0. So y equals 0 is a horizontal line. It's all the points where the y value is 0. And then, let's see what I have here. 3.2. It was 8 pounds. And 2 negative 1. That was 4 pounds. And right here, at negative 1 and 1, it was 2 pounds. So now I'm calculating vertical distances. I'm going to pause for a minute when you get caught up.
So basically, for some of the moments, you just multiply points with the weight.
Distance times weight.
For distance times
Yeah.
weight, and for total of weight, you just add.
Yes.
Okay.
Let me write that down. The moment about y equals 0 is the distance from y equals 0 times the weight. So a moment is that tendency to make it tilt in a certain direction. In this case, it's, and we get that by multiplying the distance times the weight. So what's this? The 8 pounds is how far away from the y equals 0 line?
3.
No, 2. So that's a vertical distance which is measured by y's. And this one is 1. You have to be a little bit careful here. What's this distance? So first it's a y value, and remember we want to distinguish between the different directions. So below is going to be negative. So what we're going to have is this 2 times 8 plus 4 times negative 1 plus 3 times 1. And if you work this out, you'll find the coordinates or the number for y bar. And then if you put the x bar and the y bar together, you've got the balancing point, which we call the centroid. Feel okay? We got time for an interesting example. We've got the graph of y equals 1 minus x squared. I have a feeling this might come in handy later. Because those points are 1, 0, and 0, 1. Oh, and one point I want to make, it's going to make our life a little bit easier when we're doing the calculations, is, all these shapes are going to have a uniform density. So imagine that I found a centroid when the density was 3 pounds per square foot. And then I just traced this shape onto some styrofoam which has a density of 1 pound per square foot. It's the same shape, just a lighter density. How does that change the centroid? See, it doesn't? So, I might as well assume that whatever shape I'm given has a density of 1 pound per square foot. So if the density is 1 pound per square foot, then 3 square feet weighs 3 pounds. So if the density is 1, then numerically the area is going to be the same as the weight. So whenever I'm asking for the weight of something, all I need to do is calculate the area, and I'll have the same number. Agreed? My x bar calculation. Is the sum of the moments about x equals 0. And since numerically, well, 2 reasons, is I can change the density to whatever I want. It's still going to be the same centroid. And it's numerically, if I change the density to 1, the area is equal to the weight. So the denominator is just the area under the curve. And this is what we've been doing since Calc 1. It's an integral. We'll find the area under the curve. So far, so good? To calculate the moment about x equals 0, we do the distance from x equals 0 times the weight. That's how we do the moment calculations. We've got x equals 0 looks like this, and then we're going to calculate how far that is and how much it weighs to measure what the tendency is to tilt to the right. And instead of calculating weight, I readjusted the density so it was 1. And all I need to worry about there, numerically, is the area. So we've done problems where we've used vertical slices. We've done problems where we've used horizontal slices. And since I'm calculating the distance from x equals 0, I want to take my slice where all the points in that slice have the same distance from x equals 0. So here's x equals 0. And I want a collection of points that have the same distance. Would that be a horizontal or a vertical slice? So my 2 options for the slices. I could do a slice like this, or I can do a slice like this. One of these 2 slices has every point in the slice the same distance from x equals 0. Top or the bottom? Top. So for my x bar, my slice is going to look like this. There's x equals 0. Let's put the y-axis on here. There's the y-axis. And one single slice is going to look like this. And think about this as a generic xy point. What's that distance? How far is this from the x equals 0 line? I'm just going x. It's a horizontal distance. The letter that measures horizontal things is x. And x is distance from the y-axis, or distance from x equals 0. So that's x. And is this a horizontal or a vertical distance? Vertical. What measures vertical things? Y? and y is 1 minus x squared. Is this base a dx or a dy? Dx. So it's to get the moment about x equals 0. It's the distance from x equals 0 times the area. Calculations there. And for x bar, it's the sum of all these moments. So 0 to 1 for x times 1 minus x squared dx. So the y bar calculation is going to be the sum of the moments about y equals 0 divided by the total area. And notice that's exactly the same denominator as x bar. So we don't have to recalculate this. It's whatever we had for x bar, we can do right here. Calculate those moments about y equals 0 is that's going to be the distance from y equals 0 times the weight. And numerically, the calculation of weight is going to be the same as the area. Y equals 0 looks like this. And we'll go ahead and put the x at or the y-axis here. And if I'm looking for the distance from y equals 0, if I use a horizontal slice, every point in that slice is going to be the same distance. So for the second part, I'm going to use a horizontal slice. There's the xy point. So here's y equals 0. Here's my horizontal purple slice up here. How far is it from y equals 0 to all the points on the slice with the right value of x comma y? What's that distance? That's a vertical distance, which is exactly what y measures. And the area, is this a dx or a dy? It is a dy. What's this distance? That's a horizontal distance, right? So that's x. So my moment is going to be y times x dy. And that x should look terrible next to the dy. So if y is 1 minus x squared is 1 minus y, and x is the square root of 1 minus y. So we've got y square root 1 minus y dy. And the idea here for these horizontal slices is every y value generates one of these slices. And it's the range of y values that give me the slices. And the bottom slice is here at y equals 0. The top slice is up there at y equals 1. Now look at the time. It's 3:15. Time to go. We'll be on YouTube. I'll let you know.